Okay, I think last time we talked about the pure water permeability, how we can measure the water permeability. The pure water permeability was defined as the flux divided by the pressure that you have applied between the feed and the permeate. And viscosity should be considered here in this case. If you're using water, then viscosity will be just equal to 1, so that this will be neglected. But if you are using the different solvents with a different viscosity, then this eta value should be considered anyway. If you plot the flux, the amount of liquid that is coming through your membrane with the membrane area, with a given membrane area and a given time, which is defined as a J, as a function of pressure at different pressure points, then the slope will be LP, or pure water permeability, as we defined in our previous equation. Okay. And next topic that we will talk about is about how we can characterize the membrane with the microscopes. We have several types of microscopes, the SEM and TEM and AFM, and we will go through very quickly about the nature of the microscopic the techniques. Scanning electron microscope is the one that you get the image from about the membranes. Okay? This instrument gives us the information about the structure of the membrane, whether you have a pore or not, okay? In your surface or the cross sections. And also you can measure the pore size and distributions, of course, but pore size can be precisely measured with other techniques as well. But visually you can determine this pore size. Okay? You have to prepare your samples so that this is more like a destructive method rather than non-destructive method. You need to fracture your samples at a very low temperature, because if you cut the membrane sample, then you will your fracture will show the plane about the knife. So the fracture should be made at a very low temperature, such as in liquid nitrogen, and should be very sharp. Okay? Usually they use a high vacuum mode, but these days we have the SEM with a very low vacuum, or even the atmospheric pressure, the SEM as well. That's what we call the environmental SEM. So instead of dead picture, we can see the live picture, just like a video of what's going on between the molecules, or between the phases, interfaces, or even with the live organisms as well. So environmental SEM is quite popular in the agricultural or biological systems. So the principle of this SEM is that instead of using light, in the case of microscope, you use an electron gun. So the electron beam is exposed to and passes through this magnetic field, and focused on to your specimens, and your image is coming, after bombardment of electrons to the surface of your samples, and then you collect your electrons coming from your surface, and the secondary image will be detected here through this detector, and you see from the screen. So electrons travel instead of light, and that's what the principle behind this electron microscope. Now, now this is the scanning electrons, but TM, transmission electron microscope, is the one that you have a very higher energy than this scanning electron microscope. So your sample will be transmitted through the sample. I mean, the electron will be transmitted through the sample rather than scanning. Okay? So that's the difference between SEM and TM. So the resolution should be higher for TM than SEM. Okay? This is the picture of SEM, and when you prepare your sample, such as the hollow fiber should be fractured in the liquid nitrogen. Okay? In the liquid nitrogen, which is minus 190 degrees C, 192 degrees C. If you use your tweezer, and between this tweezer you have your hollow fiber or films, polymer films usually, and put it in, and if you just pressurize them, it will give you a very nice, cross section of the membrane, and put it on top of your the mount, and coat your samples with the gold usually, and so that the electrons will be the bombard to this metal pot, okay? So that this image is coming from the metal coated one, and you can of course tilt and magnify it to get this image. The TM is a little different and difficult to handle, and TM you should have a very thin film of your sample, so-called a microtome. You use your microtome to cut your cross section of your samples, and put it into the epoxy and cut it using the microtomes, and for the same machine, not the same machine, but TM machine, you can take the picture with the same principle that we have described. TM actually see the phase separated structure of your membrane rather than surface property. Okay? So SEM is much more helpful in membranologist in showing the surface layer or the cross section of your membranes. AFM usually collects the image of your surface. Okay? So what you can see is that atomic force microscope investigates particularly the surface only. Okay? Surface of the film, surface of the fiber. You can do the surface imaging. Usually you should use a tip, okay? Tip such as needle. Okay? Needle will be touching the surface of a membrane, so that surface topology will be digitalized in this picture. Usually it's given in a color picture. So when the tip crosses the surface, it deflects the interactions. So cantilever holds the tip, and it will be photodiodized and getting this digitalized image of the PVDF membrane in this case. So tip is very important, and this is very powerful tool as well. It also shows the roughness of the membrane, and the surface roughness will be also useful determining your topology of the membrane surface. Mechanical properties are the next topic that we can say. Mechanical stability is very important for the membrane in many cases, because if the membrane is not stable upon applying to the stress, if it's broken during the operation or during the preparation of your modules, during the preparation of your membranes, there is no use. Okay? If it's mechanically weak. So mechanically strong membrane is required in the real industry, but what about the measure? What about how we can characterize these mechanical properties are the important topic as well. Usually, mechanical stability is coming from the crystallinity and orientations. So when you have a crystalline material, such as ceramic and metals, you have a pretty high rigidity and high modulus and tensile strength, whereas the elongation is a different story. Okay? Elongation is measure of the flexibility of your materials, and the flexibility, of course, is very important as well too. Usually, you can measure the mechanical property, but the other techniques such as crystallinity can be detected by the electron microscopy, particularly TM, or small angle X-ray diffraction patterns. Okay? You can see the clusters, you can see the ion gets together, or you can detect the degree of cross-linking as well using the IR spectroscopy and so on. So other techniques can be also used for the mechanical stability, but I think this time I can show you the very simple way of measuring the mechanical strength. Which was given in this picture. What it is that this is called the tensiometer, where the sample is held in one axis, and the second holder will be pulling down to your sample so that it applies the pressure and the stress. So stress is plotted in the y-axis, whereas the strain or elongation is plotted in the x-axis. So when the sample is following this line, it shows the yield point here, and then your sample will elongate it to up to about 100% of your strains. The modulus, particularly the initial modulus, the initial slope, is plotted as using the Young's equation, where the stress is equal to the modulus times the strain is Young's equation, so that from this initial slope you can calculate the modulus. The modulus is a measure of the rigidity of a material, and the higher the modulus, stronger the material that you can get. Whereas if you have a higher number of a strain, such as 100% here, this material is very much flexible, very much stretchable in this case. So as I said, initial modulus, initial slope is defined as a modulus, and is a slope between the stress and strain, and this is the final elongation at break. This is called the breaking point is called the stress at break point, whereas this point is called the yield point. This is the stress at yield point. This is the elongation at yield point. Okay? And so we have 4 points for plastic materials. In most of the polymeric materials, you can observe the yield points because of the plastic behavior of the nature of the polymers. The polymer shows elastic property and also the plastic property. So this is what we call the elastic and plastic material combinations. Okay, so that's the point where we can discuss about the mechanical properties. But from now on, I think we can talk about the ion exchange membranes. Usually, ion exchange membrane contains the charges. Right? We can have a negatively charged membrane, which is called the cation exchange membrane, or we can have the anion exchange membrane, which has the positively charged positive charges in the membranes, so that your negative ion can be exchanged. Now, we can determine these many of these properties, but particularly the charged membrane swells. Charged membrane usually swells, so the swelling property is quite important. If you have a large number of a charge density, then your swelling behavior is much more extensive. But mechanical property is quite opposite to this charge in swollen state. Okay? In the swollen state, you have other properties such as the water swelling. In the case of water swelling, we usually can characterize the three different regions of the hydrogen bonding, okay? Or swelling. For example, if you ever charge the sites, so this is the membrane with a charged site. But the water is coming out on the surface of your charged membrane. And this is what we call the bound water, which is just contacting the charged site or hydrogen bonding sites. So hydrogen bonding between this charged site of your membrane surface and the water is what we call the bound water. Okay. There might be some layers. There's some number of layers, which could be several layers, maybe 2 layers or 3 layers. Several means not just a definite number, but some number, okay, of water is bound between the surface of the membrane and the water is a bound water. So we have a number of bound water. And next, and actually we have 3 layers. Next layer is called intermediate layer. And the 3rd layer is called the free water. So when the membrane was swollen, we usually have 3 types of water present in the swollen state of your membranes. If you're talking about the highly swollen materials. How we can determine this free water and bound water, okay, is quite an important issue. And the measure of this free water and bound water was done in 1970s by using DSC, differential scanning calorimetry. Differential scanning calorimetry measures the heat capacity versus the temperature. So if you increase the temperature, you have endotherm and exotherm, so that you detect the heat changes in your given chamber. Okay? So heat could be exothermic or endothermic depending upon your state of your water and state of your materials. At 0 temperature, at 0 degrees C, there are some exothermic peak, usually. If you have a water and water was frozen, usually you have some sort of exothermic peak, and the area under the curve will depend upon the amount of water. So if you have a large number of water, then your water will be much more, the area is much more bigger. And if you have a smaller amount of water, a small swelling degree, then the area under the curve is smaller, okay? And if you go down further to maybe minus 30 degrees, minus 50 degrees, something like that, depending upon the material, of course, you may experience another peak. Another peak, okay? So, for a swollen material of a polymer, by decreasing the temperature from room temperature down to minus 100 degrees C, if you can detect some enthalpy changes of your peak, and that is due to the water, usually. Particularly when you observe around 0 degree, it's not exactly 0, but it's around 0, because this, the maximum or minimum peak temperature is not correlated with 0 degrees C because of the cooling rate or heating rate. So the rate will be changing, of course. Anyway, if you slowly cooling down, then if you observe these two peaks, then the first peak is due to the free water. The second peak is usually due to the bound water. What about intermediate? Okay. If you measure the free water content and the bound water content, and if you observe the swelling, the total water content at room temperature, okay, is free water plus intermediate water plus bound water. And you measure the free water at room temperature, right? That's what the swollen state. The free water is measured by the DSC. Bound water is measured by bound water here, content here. The rest of them is intermediate water. So this way, you can break down your water at a given state, particularly the highly swollen material membranes, particularly the hydrogels and ion exchange membranes, and these. These free water contents and bound water contents are very important in many cases, just like ion exchange membrane or fuel cell membranes or charged membranes. Usually, if we break down into three, although it's not easy, but you need a very highly, endurable experiences and times, although it's time consuming, or if you can get those the breakdown of your water contents, it will be much more informative in analyzing your data. And DSC is widely used in measuring the different state of water. You can measure whether you have bound water or not by using the infrared spectroscopy, because infrared spectroscopy usually measures the hydroxyl group. If you have a water, then it appears around the 3,300, absorption peak, and this peak is usually coming from hydroxyl. If your membrane does not contain any hydroxyl group in your polymeric structure, but observe this hydroxyl group, that should come from water. Whether it's coming from water in the air or water in the membrane. Okay? So if you block the water in the air from your environment, then if you still observe this hydroxyl group, then it's usually coming from the water in the membrane. This way you can detect the water contents and water state, of course, done by the NMR as well. I'm not going to go more in detail about the NMR, but these are the techniques that you can measure the state of water, so-called the free water, okay, and the hydrogen states. Usually swelling. If you have a swelling, the swelling usually gives you the higher volume of your membranes or hydrogels. Okay? Swelling and deswelling. Swelling and deswelling is a measure of your capability of your membrane to absorb the water. Okay? If you think about the higher, 기저귀, diaper. For the baby, it absorbs a lot of moisture, a lot of waters. Okay? And those diaper contains a cross-linked polymer. The cross-linking occurs between in the main chain of your polymer, so that when you have a capability to absorb the water, whether it's a free water or bound water or whatever, then it will be swollen. The swelling usually lowers your mechanical property for your linear polymer, but if it's a cross-linked, then it's a different story. Okay? It's a little different story. Okay? So the swelling will change your mechanical property, but the swelling depends upon the number of ionic groups that you have, number of ionic groups, and number of hydrogen bonding capability of your the membranes. This depends upon, of course, the cross-linking density, homogeneity of the membrane, and so on. And if it's a swollen, then tensile strength will decrease, and permeability, of course, particularly the water permeability, will of course increase because of the swelling. So the swelling is very important. Usually the swelling is measured by the simple equation where you measure the weight of your dry sample with the complete dryness, where you measure the weight of your wet sample, and percent swelling could be defined as a delta the W, which is just the water, right? If you subtract the weight of the wet sample minus the weight the dry sample, then this is just the water. Okay? How many water that you have in your wet membrane is the measure of your the percent weight of your swelling. So this is a very simple equation that you can use. Of course, you have to equilibrate them. Okay? You have to equilibrate the water into your membrane, of course. And this is very important, the swelling property measurement in this case. What about the molecular weight cutoff? Okay, I told you that we can measure the molecular weight cutoff, but let me define first of all the rejection. Okay? The rejection could be defined in several ways. Okay? Now, usually the rejection by the sieving mechanism is defined as from this equation here. The rejection is a function of radius of your solute with the radius of your polymer. Okay? In other words, radius of your pore in your polymeric membrane or membrane is defined as RP. RS is defined as a radius of your solute. If you have a smaller solute and larger solute, the smaller solute through this pore could be easily sieved through, whereas large molecule or larger than diameter, larger than this, the length of this, the pore of your membrane cannot go through, is called the sieving mechanism. And you can calculate the rejection from this equation as well. Molecular weight cutoff usually uses the rejection, of course, with a different story. But rejection is defined as concentration of your I component from the feed and from the permeate. Okay, so for example, if you use dextran as a standard material, you make the standard solution for a given molecular weight. For example, molecular weight of 500, molecular weight of 1,000, molecular of 100, molecular of 1,000, molecular of 10,000. So if you have 3 or 4 or 5 different solutes, okay, which is defined as I, then you feed those solution with a given concentration CF, okay, and through those membrane you measure the concentration of the permeate, CP, okay? CPI, CPF, and CPI was measured here, and calculate them. So at this point, you do not have any rejection, meaning that you feed your concentration of 0.1% usually is coming through the permeate, and you can obtain the 0.1% as well. So it will be canceled out. This should be 1, so R is equal to 0. So if you have a smaller sample, the molecular weight or diameter, then you do not have any rejection. If you have 1,000, then you feed, and the rejection is let's say about 20%. About 20%. So you see CP is about 80%, in fact. So total will be about 80%, 10%, excuse me, and so on. And then you plot them with 4 or 5 different standard samples. And the molecular weight cutoff is defined as a solute molecular weight at a 90% of a rejection. Of your solute is defined as a molecular weight cutoff. So using the different, at least the 4 or 5 different, different molecular weight of water soluble, particularly water soluble solutes, if you are using the amicon cell or Frange cell, and you fill with the solute in the feed, using the dead-end filtration cell, if you pressurize them at a given condition, of course, this depends upon, of course, the pressure and the concentration. So there is a standard conditions at room temperature, and then you measure the concentration of your permeate from the feed and the permeate of a concentration. Then you calculate the rejection and plot with the different the molecular weight and give your 90% cutoff is called the molecular weight cutoff. You can have a sharp molecular weight cutoff or a broad molecular weight cutoff, depend upon your pore size distribution, pore size of a membrane, and so on. And so, there is a standard method. The pressure is 100 kPa, and concentration is 0.1%. Temperature, of course, will influence your permeation property. So this was set it at 25 degrees C. Molecular weight cutoff is influenced by the shape of the molecules. Of course, if the shape of the molecule is spherical or the hexagonal, that influence the molecular cutoff as well. Usually water-soluble dextran is widely used. You may have a sharp molecular cutoff or diffuse or molecular cutoff. But anyway, this is the raw data. So 90% of your the retention is called the molecular cutoff of your membrane. This is very important for ultrafiltration membranes. Ultrafiltration usually provides what is the MWCO. MWCO less than 1,000 is very difficult, particularly a few hundred is very difficult to make the ultrafiltration membranes with a very sharp molecular weight. And this few hundred Daltons of molecular cutoff is important, particularly in the hemodialysis. Hemodialysis membrane usually filters the blood for the kidney disease patients, okay? Because urea or creatinine is produced from our body, and creatinine and urea should be discharged from our kidney, okay, through urea, through our urine. But if our kidney as a filter does not filter our urine or kidney, the urea or creatinine, then the urea or creatinine toxic material will be accumulated in our body. So your color of your body will be turned into black, and it causes a lot of other diseases. So it's very important to remove those the byproduct creatinine and urea. And those kidney disease patients should go to the hospital at least 3 days a week, okay, 3 days a week or 12 hours a week to filter their urea and creatinine in ex vivo. So usually, if you are making a very nice membrane with a very sharp molecular weight cutoff, just right for the hemodialysis, then that's very important. Usually one dialysis time takes about 4 hours, and if you can reduce those hours, the duration of your hemodialysis from 4 hours to, for example, 1 hour, that helps a lot to the kidney disease patients for their life, quality of their life. The next topic that we can talk is about the bacterial challenge test. Usually, bacterial challenge test of the membrane has been done by many of the membranes using the specific microorganisms such as Pseudomonas diminuta, and this is one of the bacteria. So the bacteria is intentionally supplied to along with the feed, so that the bacteria can attack this polymer intentionally. And after some time, they remove these bacteria, remove this membrane, and see what happened. Okay, whether this bacteria can eat the membrane or not is a bacterial challenge test. And this bacteria test is important, particularly for water application. Bacteria can eat these, the particular polymers, and after some time, you may cause a lot of trouble because of these bacteria. Let's talk about the pore size measurements. Okay. Well, pore size. You saw the pores of your membranes. And the pore size is very important. And size of the pore can be determined by many methods. if you assume that you have a pore, then this pore can be observed visually by, of course, microscopic measurements or characterization methods. Or if you cannot see, then you have to measure directly, okay, from several methods. We can use gas, or we can use a liquid. We can use gas and liquid, or liquid and liquids. So I will show you some of the representative methods. This is the what they call is bubble point test. And bubble point test is based upon the liquid which is held in the membrane pore. Okay, so that if you have a pore, this pore is filled with the liquid. Okay, first of all, filled with the liquid. And then you pressurize the membrane, and so that the liquid will come out. Okay, liquid will come out. And when the liquid is coming out, the first time or first pressure should be related with the radius of the pores. So radius of the pore, RP, is defined as 2 times the sigma, and sigma is defined as what? Sigma is a contact is a surface tension. Okay, sigma is the surface tension, and the phi is the contact angle, right, between the liquid and the pore. And P is the applied pressure. So when you okay, so when the contact angle is 0, then cosine theta is 1. 0 means that if it's water, then it's water. Then you can cancel this out because it's cosine theta is 1, and then you can calculate the pressure. You can measure the pressure that the liquid is coming out, and if you know the surface tension, then you can calculate the radius of your pore. Okay? So this way, this is one of the method where you have your alcohol and water mixture through this hydrophobic membrane, which was swollen. So you wet the membrane first and put it into your membrane here, and apply the pressure. So you measure the pressure or the bubble that is coming first of all, and then you measure the pressure of the first bulb is coming out, and that's the pressure P that you measure. And by knowing this surface tension and contact angle, then you can calculate this RP. Usually, your instrument will provide you automatically the RP in this case. Instead of liquid, we can sometimes use the mercury to measure the porometry, pore size. Pore size and pore volume and pore size distribution and density can be measured by the mercury porosimetry for the dry membranes. It's not the wet state. Okay? So if you are using a non-wetting property of the mercury, then this is the way of methods. So mercury is filled through the pore, okay? And if you apply the pressure, mercury will come out for non-wetting membranes. So this is one other technique that is similar to the bubble point methods. We have gas and liquid displacement ways where the liquid is filled and the nitrogen is pushed out. Okay? So nitrogen will be filled with the liquids, and this is what this is similar to what you have seen the bubble point method, and from the equation, then you can calculate the radius of the pore and the pore size distribution and so on. I think we have this machine in the laboratory. Yes, this is the PMI method, capillary fluorometer. and you apply the pressure, such as a nitrogen pressure and gas flow, so that the first point is called the pore that is coming out, and so on. We have a liquid displacement method. Usually they use water and isobutanol as a liquid and liquid. What it is that once you fill your one liquid, and the second liquid will replace the first liquid. And the pressure is about the same. By using the same similar equation, then you can calculate the radius of the pores. They use a HPS pump, membrane, module or membrane or whatever, then measure the distal balance and record. So depending upon the liquid and gas, for a given membrane with the same pore diameter, 10 nanometer, there is a different pressure difference. Okay? For example, for the same membrane, it applies for the mercury parameter. It uses very high pressure, whereas water and isobutanol, liquid displacement, uses very small pressure. For homogeneous membranes, we use sorption and diffusion measurements. We can determine the glass transition temperature. For ion exchange membrane, we can measure the electrokinetic property, and so on. Permeability and selectivity are the very important property in the gas separation membranes. Of course, the sorption and diffusion is important, and I think we can discuss about this later on in the gas separation session. Glass transition temperature the glass transition temperature can be measured here in this case. But before we go with the TG measurement, you can measure the contact angles. Contact angle is defined as angle between the surface of your membrane with the contact angle between the liquid and the membrane, and this is defined as theta, and theta is the contact angle. Lower the contact angle is from your water, then hydrophilic the membrane is. Whereas if you have a larger or higher contact angle, then your hydrophobic is the property of your membranes. We have dynamic contact angle measurements, and using the Young's equation, of course, you can measure the contact angle as well. Usually, 150 degrees C is the criteria for superhydrophobicity. Okay? So if the membrane has above 150 degrees C degree of contact angle, then it's regarded as superhydrophobic, as written in here in this case. And the lotus leaves have above 150 degrees C, 150 degree, not degree C, of a contact angle. So the water will be repelled and the flow, and that property, superhydrophobicity, is coming from not just the membrane, not just the material property, but the configuration of your pores. Configuration of your surface has a very rough surface, so that water actually will not go touch with the deeper valley of the membrane pores. TG can be measured by DSC. If you increase the temperature, then the delta H will increase, so that the midpoint is defined as a glass transition temperature of your endothermic the heat of enthalpy, And the crystallization and melting temperature can be defined and measured by this very nice technique, DSC. We can measure the ion exchange membrane properties because this membrane has a charge. Electrical charge can be measured. Electrical resistance can be measured as well. Pump selectivity of the membrane is very important because if you have two different ions, positive ion and negative ions, just like the rejection, we need to know pump selectivity of the membrane for different ions. Transport of water is very important as well. Mechanical property has already been touched, particularly in the different electrolyte solutions. Not just the water, but we are dealing, if you are talking about the diaper, we are dealing with the ionized solution rather than just the pure water. So at different pH, at different electrolyte concentration, the stability of the membrane is very important as well. Usually the charged membrane can be easily detected by the chemical methods. When you have an ion exchange membrane containing ammonium group, then by adding the color, the titrating agent, usually color changes. Color changes as well in the cation exchange membrane containing the sulfonic acid group by using the methylene blue and methyl orange, the same one, color changes from yellow to blue in this case. So this is very simple way of just detecting whether you have the charges or not, but you do not know how many, what is the density of the charges in this case. Hydraulic permeability of the membrane is very important. If you have pinholes and defects, usually you do not have any rejections. Okay? The water permeability is very high, and pinhole or defects is easy way of measuring your stability of the membranes. Long-term stability of the membrane, particularly in the chemical, is of course important. Usually for ion exchange membranes, we use a Fenton's test. And Fenton's test utilizes the oxidizing agents and degrades the membrane in a very harsh environment. And the time for membrane integrity is a measure of your chemical stability of the membranes. We can determine the electrochemical property of the membrane, particularly in these terms. Okay? IEC, electrical resistance, and pump selectivities. So from now on, I think we can discuss. But I think I have invited Dusong to discuss further on about just a second. I know you are ready, but I have asked Dusong to explain about the impedance spectroscopy. Let me discuss with you about the IEC. IEC of the membrane can be measured by the sodium hydroxide or HCl by titration. So using the titration method, you can measure the ion exchange capacity. Okay? We can determine the electrical resistance. Electrical resistance of the membrane can be also very important. It is expressed by the current density, which is expressed as watt per square meter or watt square meter or watt square centimeter, stuff like that. And electrical resistance of the membrane is determined by the IEC and the mobility of the ions. Okay? We can have an area resistance. We can have a membrane resistance. We can have a cell resistance. We can have a total resistances. So resistance of the membrane is particularly of interest because we can eliminate the other environmental resistances as well. So this is one of the examples of the instrument using the direct current, DC, And what you do is that you fill the membrane. You put the membrane here. You put the membrane and fill the solution. And the membrane surface is connected with some solutions containing the KCl, and electrode, column and electrodes is connected to each other. So the test solution is floor, okay, and the potential drop is measured by using this type of instruments, and using these capillaries, which touches with this membrane. Without the membrane in the test cell is measured by the current density passing through the cells, and you measure the resistance of the membrane with the solution M plus S as a slope of the current density, the voltage divided by the current density. So if you plot, for example, voltage with the current density, and the slope will be the total resistance, RMS, and RMS is addition of membrane resistance and the cell resistance of the solution resistances. So by measuring the RMS, and if you know the resistance of the cell, then you can get the membrane resistances using these equations. AM is area resistance, and R is just a resistance in this case. Usually the area resistance AM is almost constant, okay? And it's not dependent upon the current density. We can also detect the resistance by using the AC mode, alternating current mode. Membrane resistance can be detected by the specific resistance of a cell, which is very similar to what we have described in the DC mode. And I think I have invited Do-sung to explain to us about the impedance spectroscopy.